Hello guys, am I audible?
No, you also, yeah.
Yes, sir.
So yesterday I gave some some questions to solve. Anybody who has solved?
Yes, sir.
Yes, sir.
So any question you would like to discuss today, like out of those 3-4 questions? So let me just quickly do the square problem. So you got all the questions correct, like you got all the answers, or you have some doubts in any one of them?
Sir, no, I got answer.
For a cube also,
Huh?
you got answer for cube problem.
Cube, only square and hexagon was there, no?
There was a cube also.
Oh,
Okay, anyway.
sorry, sir, I didn't say
That's
that.
fine. If you have done these two, that's really good. So what we can realize, if I choose one of the charges, we can clearly see that the adjacent charges will repel. So the top will repel down and the right will repel left, right? And the third charge, which is not adjacent, rather it's diagonally away, will also repel, but in this fashion. Now what we can say, the adjacent forces must be equal in value because they are having same separation. But the diagonal charge is not at the same separation as the adjacent elements or the charges. So we must name it differently. Let's call it F2. And what you can see or understand that the F2 itself represents the line of symmetry. Do you realize this? F2 itself represents the line of symmetry.
Yeah.
And therefore, to find the net force, what we are supposed to do, we are simply going to find the component of force along the line of symmetry. Okay. So what we can say, that F net equals to F2 plus, what about the F1? So what we can write, F2 plus. Now take the component of F1 along the F2. So what is the component of a vector along the F2 direction? Am I audible, guys? Yes or no?
Yes.
Hello, hello. Am I audible?
Yes.
Yes. So tell me the answer. No? What is the component of F1 along the line of symmetry?
So,
Yes.
KQ by A square. No,
What did you say?
KQ by A square.
No, I'm asking something different. I'm asking what is the component of F1 along F2?
Oh,
Cos
First question is yes. Yes, ma'am, tell me.
cos theta.
So what should I write? Tell me completely. No?
sir, F cos 45.
F1 cos 45.
45.
And we have two such forces. Can you multiply by 2?
Yeah.
And now we have resolved all the forces along the line of symmetry. So this is the net force. No need to solve further. And now you can substitute the value. What is F2 by the way? kq square upon
by 2a square.
very good. And what is f1?
Kq square by square.
So the net force turns out to be how much?
Kq square by 2a square 2 root 2 plus 1.
1 by 2 plus root 2.
Yeah.
Okay, so that's the answer. So I hope those who have got the answer must have got this answer. The other way, I will just start the first lines. The other way of doing is write every force into vector notation, I cap and j cap. You can choose some suitable x and y coordinate on your own. So this is the something which you need to think about yourself, like how you're going to choose the coordinate system. And you can write as f1 minus I cap, f1 minus j cap, but f2 is in the third quadrant, so it will have f2 by root 2 minus I cap minus j cap. So I have taken the component and written the I cap and j cap directly, and then you can solve it, rearrange it, and do whatever you want. All right. Also, you can see numerically that f2 is f1 by 2, because the root 2a square becomes 2a square, which is exactly half of the net, force due to the adjacent charges. So the adjacent charges applies force double the diagonally opposite charge, as it is obvious from the values. Okay. So similarly, now we can solve for the hexagon. Oh, this is not required at all. So we have charge at every vertex. A little bit of geometry and you're done. So you can find the force on any one of the charts. I will choose this one. No matter which one you choose, the answer won't change. So here we have, of course, two adjacent charges which will apply force like this: repulsion and repulsion, right? Then what we have next? The next two charges which will again repel, and then the third charge will be alone, pushing like this. Now, how to make the nomenclature, like how to name it, like which one is what? So the distance, because the charges are same, so we only look for the distance. So we can name it the first force as F1 F1. Then we can say F2 F2, and then F3. Now you guys tell me Do you see the line of symmetricity for the resultant force?
Yes, sir.
So what that would be? Which force is the line of symmetry?
F3.
F3.
Excellent. So this is the line of symmetry. So now because you can see it, your next job is pretty much simple. Just find the net force along that line, which means find the component of force in that direction if it is not in that direction. If it is in that direction, just add it. So hopefully you can tell me what should I write here, the net force. Anyone would like to say something?
Sir,
Tell me
about
guys.
which
Pardon?
about which force?
About which is what? We are finding force on this charge.
Oh, yeah.
The net force acting on this charge, right?
Yeah.
So
So
what is the
2F1 plus 2F2 plus F3.
Oh, so you understand force is not a scalar, no? It's
Yeah,
a
yeah.
vector. You have to be careful about the components. In which direction you can add? Vectors can be added together only when they're in the same direction, isn't it?
Yeah.
So the net force is going to be in which direction? So what is the line of symmetry in this case?
F3.
So you're supposed to resolve every force in the direction of F3. Are you doing it?
Yeah. Oh, sure. Can I have made a mistake?
So you have to understand it's a vector and you have to find the angle first. Find the angle, then try to derive it. Okay.
Yeah.
So I think yeah, 2F1 cos 60 plus 2F2 cos 30 plus F3. Correct. That's the right answer. And now you are just supposed to substitute the value of F1. F1 is KQ square by A square because it's the nearest location. What about the F2? How far are these charges? What is this? In hexagon, this is 60 degree.
Yes.
So this is 30 actually. So this is also 30, 30. So can you find X now? Now it's easy. No. So what is F2 guys? Tell me quickly what is F2?
KQ square by TA square.
KQ square by how much? 3 or 2?
Yes, sir. 3, sir.
Very good. That's the right answer. What is F3 now? KQ square by what is the separation?
A square.
How much?
Uh, A square in denominator.
A square. Now what is the F3 separation from the charge? Huh? What is this separation? In a hexagon, what is this value? Y. The F3 is acting between this charge and this charge, isn't it?
Yeah.
So what is the separation as per the diagram? Can you tell me the separation at least? So you do not know about polygon. So what is the separation, guys? Come on. What is the separation from here to here?
2a,
Yeah, of course it's 2. So what is the force then?
4a square.
4a square. This is what I was waiting for. So what you have written is correct. So now what you are supposed to do, just substitute the value, and once you substitute, you're done. Okay. Okay. So if you want to can solve now, you can just substitute the value, you can get the answer. Now this one is really difficult, which is the Q problem. But you need to learn something like this. Or if you are not comfortable with this method because this is the easiest one, you can do it by the long method of vectors. So write the coordinate of every point, write x cap, y cap, sorry, x and y component of every point, find the unit vector, express the answer in vector notation, add all values. That is a hell lot of task to be done. But if you are interested, you can do. No one is going to stop. So what if we have a cube? You have to be patient enough to solve these sort of numericals. Never get like, if you get bored out of solving this, it will be really bad. Now, if we have a cube of side length A and every vertex will have a charge Q, okay. Now you can choose any charge to start your analysis. So which charge I should choose? This one. Doesn't matter. So first of all, every vertex will have how many adjacent sides in a cube?
Sir, can you repeat the
Three.
question?
How many adjacent sides are there in a for a vertex in a cube?
3.
Three.
And how many the next distance will be like 3 adjacent and then 3 face diagonal
Yeah.
and 1 body diagonal, right?
Yes.
3, 3, 6, 1, 7, and 1 itself is 8. 8 vertex is done. So the adjacent will repel like this: 1, 2, and 3. So these are the 3 forces from the adjacent sides. Is this clear, guys? Maybe.
Yes.
Very good. So if you have understood this part, then I'm really glad. We can go to the next part. So these are the 3 forces which are equal in magnitude, but you can see they have. If I call F1, this must be F1. So all 3 can be F1, isn't it? Of course, we can say.
Yeah.
Whether you like it or not like it, we can say. After these 3 are done, we are done with the adjacent sides. We have to study the face diagonal. So this will repel like this. Difficult to see, but all right. Oh, this looks nice. one face and other third face. All right, so slightly difficult task to understand. Huh? And one is like you can't see it because it goes in this direction. This goes in this direction. But what we can understand that over these are again three forces acting in a way which eventually creates the line of symmetry. And the third force, which I'm taking the body diagonal, which will exactly go towards this end. Again, difficult to visualize in this picture. But looking at all forces, can you say something? Can you comment about these forces? Can you see the line of symmetry? Anybody?
Sir, red line.
So the red one.
Yeah, the body diagonal.
Yeah, that.
So we need to resolve every other force along the body diagonal, correct?
Sir,
So
it's the red
except,
line, right?
pardon?
Red line, no? The
Yeah,
way of the.
yes, yes.
uh,
You know the meaning of body diagonal? Anybody who doesn't know? Face diagonal, body diagonal, and the edges in a cube. Do you understand?
Yes, sir.
Okay, great. If you don't understand, look at the wall in your room. And for every wall, we have two corners, right? Which are diagonally away. That's called the face diagonal. Face means the wall of your room, and diagonal of that room, that wall is called face diagonal. But if you consider the entire room as a whole, and if you choose the two farthest corners, then that must be the body diagonal. Understood?
Yes, sir.
The farthest corners in your room, which you can think about, that is the body diagonal. Now the question is, it's very difficult to look at this picture and try to solve because we do not know what is the angle that these forces must be making with the body diagonal. We have no idea. Okay, we have no idea. So what we do is in a cube problem, because this is the first time you are coming through the cube problem, let's try to learn some more basic about the cube, some properties about the cube and how to deal with, because you are going to face it more regularly even in other chapters. So this cube problem is not a unique problem for this chapter. Rather, we'll see that every chapter will have some sort of cube problem. Okay. So now in a cube, if I just choose the three sides, now tell me guys, the red line represents what? The red represents which diagonal? Face, body.
Face diagonal.
Face diagonal. Very good. And if I draw the green line like this, can you tell me what this line represents?
Body diagonal.
Body diagonal.
And if you look carefully, that's not very difficult for you guys to understand. This is the edge. And do you see it's a right angle triangle? Which two sides are mutually perpendicular? The base, the red and the orange, isn't it?
Yes.
So can we say OAB as the right angle triangle? Can we say yes or no?
Yeah.
So we can find all the angles, isn't it? Can you find this angle? That's called alpha. This is 90 minus alpha, but anyway, I can call it beta. And this length is how much? A. What is the length of the red line? Please, guys, tell me. What is the length of the red line?
Uh, uh, um, root 2A.
Root 2A.
And the green line? Use Pythagoras. Come on. So, what is the length of the green line, guys? Please tell
Root
me.
3A.
Very good.
Yeah.
So, once you have all the values, can you find the cos alpha? What is cos alpha, guys? Tell me.
Root 2A by root 3.
What is cos beta? Please tell me quickly.
A by 1 by root 3.
Very good. Now I just need cos alpha and cos beta. Why? Because every the angle between the edge and the body diagonal is beta, right? And the angle between the face diagonal, the angle between the face diagonal and the body is alpha. Simple. Okay. So any force acting in this direction, what will be the component along the body diagonal? F2 cos alpha. And any force acting in this direction, which we call the edge, what will be the component along the body diagonal? F1 cos beta. Do you realize this? Difficult to see in 3D, but you can see at least in 1D. I mean 2D. It is clear? The angle part is clear, guys?
Yes, sir.
Yeah.
Yes.
Now, once you are clear with the angle, then we can directly write the answer. F net equals to, look at this very, very carefully. The F3 will have no component because F3 will be along the body diagonal itself, plus the F1 will have 3F1 because we have three such values. 3F1 cos beta. Why beta? That is the angle between the edge and the body, and that is same for everyone. So although I have shown for one, but it is true for all. It is clear? So if you have not watched the vectors, I mean, you should watch the vector lecture. You can realize all these things are very basic. These are called the direction cosines, right? And then 3F2 cos alpha. So what is F1, F2, F3 value? Let's find. What is F1, by the way? So can you substitute the value and get the answer directly now?
Yes, sir.
So you know alpha, you know cos beta, you know F1, F2, F3. Just substitute and get your answer. So a bit computationally long, but I won't say it's a very challenging or difficult once you understand the angle part. So, I hope this is clear, guys.
Yes, sir.
All right. So F1 is this much, F2 is this much, and F3 is this much, and we are done. So we can go to, and I hope that you have written the values after substitution. What is the final answer, guys? If you all have done, tell me the last answer. What should I write here? KQ square by A square common, and then what we have left with?
Sir, 1 by root 2 plus 1 by 3 root 3 plus 1.
Anybody else who, who can also match the answer? Anybody else getting the same answer? Okay, no one is getting the answer, which means you haven't written it. Okay, anyway. No.
Sir, is this correct?
I haven't checked it, so that's why I was asking. Okay, I can just substitute the value.
Sir, no problem. I'll check.
Oh, anyway, like, you can check it when I can give you the quick. Let me do it anyway. Okay, F3, F1, F3 is how much? By 3. 3 cos beta by F1. That's it. 3 F2 cos alpha. So 3 cos alpha is root 6 by 3 by 2. Yeah. It's 3 by 2, I think, under root. Right? This is the answer. 1 by 3 plus root 3 plus 3 by 2 under root.
Okay, sir.
Yes, sir,
I'll
I'm
check.
getting that.
I'll check once.
So now we can go to the next part. Okay, so these Q problems are very famous and you have to actually practice these questions. There is a vector method also, which is a bit lengthier, but not, I would say, difficult. You have to just keep on writing by writing proper coordinates and so on. So we can go to some other problems quickly. So this is an equilateral triangle, and in a shape of a star, as you can see, and this will have a charge like this, plus 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 on these three vertex. It is quite symmetrical, and the bases are parallel to each other. So this is parallel to this is parallel to this, and this is parallel to this. So let's say we have charges here. Uh, so we have a star shape object, and we can say we have 3 charges here. The magnitude of each charge we call Q. And they have common center. So the centroid is same for both. And there is a charge that's called Q naught, which is at the centroid. Okay. So the question part is clear, what we have and what we don't have.
Yes.
The side length is side of triangle is A. So the side length you can take as A. Can you solve? Okay, can you find the net force on Q naught? Oh, it looks weird. Q naught. Fine. I think I made the ostrich anyway. Nevertheless. So anybody trying this question?
Yes.
You are supposed to find the net force on the charge at the center, and what you need to remember that the center is common for both the triangles. Okay. So only I'll give 2 more minutes, then also.
Hello. Hello.
Yes, yes. Tell me.
Is it 18 q kq square upon a square?
18,
No. 18.
18 maybe. I think 18. No, I think 12, maybe 12, 16, something like that.
4, 12.
Look at the distance carefully.
Sir, can you do it?
Yes, yes.
Not understood.
Right. No, sir. I've mixed up the distances.
Okay, so you can just think of one triangle and you will get the answer. Can you got some answer? Something? Okay, all right. So let me show you. Oh, this is not good. So now if you just think of one triangle, and that is sufficient to understand. The top three are positive, bottom three are negative. So the force will be all force will be acting downwards, right?
Yes.
So if I do the centroid, this is the centroid. This will repel like this. It is like this one is repel. At the same time, the negative will also attract this one. And because of symmetricity, they must be equal in value. So every force will become double arrow. Top, bottom, all will be same. You can see. And
Yes, sir.
this and the opposite charge will attract, right? Like this. And if I call one force, just one force between the this charge, if I call only one force, if I call this force as F, you can see we have 2F here, 2F here, and 2F here, right?
Yes.
And this angle is how much? It is 60 degree.
6.
Not difficult to imagine. This is
Yeah.
so for that you can just think of this. This is angle bisected 30. 90. This is how much? 60.
Yes.
Now this is clear. It is 60.
Yes.
So the net force will be again. We can see we have the clearly a line of symmetry. So the net force must be on that line. So the 2F is already in this line, and the remaining 2F will have cos 60, which will become. Okay, let me still write down all values. So this entire term turns out to be 4F, right?
Yes.
Yeah.
See, so easy. And F is the force between just only two charges. K, Q not by the distance square. What is the distance? This one.
A by root 3.
Correct. So R cos 30, if you look carefully, is A by 2. So R is A by root 3, which is obvious the right answer. So the answer becomes A square by 3. Correct?
Yes.
Which is
Yes,
12
sir.
K Q naught by A square.
Oh.
So you have to be, good with using the symmetry. There are many questions in JE which are based only on symmetry. Like if you see the any past year problem of IIT JE, all can be solved just with the help of symmetry. So the line of symmetry is the way the net force is going to act, and therefore we are only supposed to find the component of forces in that direction. And once we have those forces in that direction, we can just add them or subtract them as if they are parallel or opposite to get the answer. Is this
Oh,
clear?
sir,
Yeah.
but did we solve the Q problem? I joined now.
Yeah.
Okay. I actually had doubt in this.
Yeah. So what I'll do is we solve all three problems. So you can
This
just,
two I got. Okay.
yeah. So what I'll do is I'll send the
Yes.
today's lecture. You can just watch it.
Yeah.
All right. So any doubt in this, guys? Anybody?
No.
No, sir.
So the next part. So we can go back to something called equilibrium. 2D problems. So we have the hanging problems. So from a ceiling, we suspend the two pith balls. Have you heard the name pith balls?
Yeah, the type of problems were there in H1. Yes.
This is the problem number maybe 23 or 20.
Yeah, yes.
So how many of you have started solving SCV?
Me. I
Yes.
completed till
Sir, I
30.
have.
Yeah, I think Kanu
Sir,
has completed already. Krish, how many you solved so far?
Sir, I have reached 23.
Very good. And Manasvi beta, how much
Sir, I haven't done it.
you haven't started also?
No, I just looked at it and then after that I'm planning
my-
to do it tomorrow. Like I
Okay.
went through quite a few questions. And then,
Not an issue. So I will suggest that okay, start doing it because as we move into the next topic, the burden will be too much because the portion we can complete at one go, and suddenly we'll see that there is a lot of question that you can solve.
yes.
Okay, so you have to be extra now effective now. So we have pith balls. So there is a small history. What is pith balls? So basically, these are styrofoam. You know styrofoam? We call thermocols.
Yes.
So these are very lightweight. I mean, they're now you know that styrofoam is very lightweight. So what they do is in the earlier time for performing electrostatic experiment, the pith balls was very common. So they used to take styrofoam balls which are very light in weight, and they used to gold plate. It's like you're spraying the gold plate over the, I mean, this styrofoam. So a lightweight and a conducting. Okay, that's how we used to create it. And these were called pith balls. And the entire history of electrostatics is having the is to do with something like pith balls. Okay, so Coulomb actually derived the formula using the pith ball experiment. Okay, this particular experiment came from there, and now we just solve as a simple laws of motion problem. But the history is really like interesting. If you go back to history, that how this all started, it is really interesting. So now we have two silk threads, and of course, why silk? Because we want insulators. So we assume the length of the string as L, and we have two pith balls. So before we solve, we will do some conceptual parts. Now let's say if I give charge Q1 and if I give charge Q2, and if the mass is M1, if the mass is M2, and if this angle is alpha, and if this angle is beta, okay, although I have drawn it symmetrically, my bad. Now the question is, for what values of M1, M2, Q1, Q2, alpha and beta will be equal. So
When they both are equal, right?
for alpha equals to beta, what must be equal? Charges, mass, both.
Mass.
So the first part is M1 equals to M2, B is Q1 equals to Q2, C is M1 not equals to M2, but and D So out of four options, which are the which of the options will make sure that the alpha and E is equals to beta? It is
M1 should be equal to M2.
yeah, that's correct. Anything else?
No.
If A is correct, then D is also correct, na? But
Yes.
but we cannot say the Q1 is not equal to Q2 because the equality does not depend on charge, right? So why the equality does not depend on charge? The answer is simple. No matter what charge we choose, the net force on each pith ball will be same, correct? Because the force on the pith ball due to charge will be the Coulomb force is how much? K Q Q2 by R square. So what really matters is the product of charge, not your charge or my charge. It's product of charge. So charge is having no relation. Just mass will decide. So if M1 is more than M2, what will happen? If M1 is more than M2, then alpha will be more than beta, less than beta, equals to beta. Can't say.
Beta will be more than alpha. Option.
Yeah. So if M1 is more than
Yes.
then beta will be more than alpha. Very good. And okay, now you're done with the theory part. So if heavier the mass, is smaller the angle, right? Because gravity will pull it back or pull it down. Okay. Now we are going to solve numerical when the pith balls are identical. So what if the pith balls are identical? So if pith balls are identical, so we have same mass, so same charge. So I will assume the case when the mass of both the pith balls are same, and so are the charges. So now because if I assume the charges are equal and masses are equal, then the alpha must be equal to beta. So can we say this is just theta? That's better.
Yes.
And if the length is L, so the repulsion will separate them by some value, and both must be experiencing the repulsive force left and right. Hmm?
Yes.
Now let's say I'm assuming that okay, I have no idea about this uh, Coulombic repulsion. Okay, I have no idea. But if it is at equilibrium, then the gravity acting on the pith balls and the repulsion must be balancing each other, correct?
Yes.
So given this equilibrium diagram, can you tell me something about the relationship between the F repulsion and gravity? So you can do it by variety of methods. So you can call the tension resisting as T, and then we know how to resolve forces.
So FR is equal to mg tan
mg.
theta.
Correct. Very good. Very good. So you can see clearly that T cos theta is balancing the gravity and the T sin theta is balancing the repulsion, right? And I need not to draw it for the other pith wall because it's a symmetrical case. So do it for any one pith wall and you're done. So for equilibrium, so we write these two equations. We write the balancing equation like the summation of net force along x equals to 0 and summation of net force along y equals to 0. And once you do that, you'll get the answer. T cos theta equals to mg and T sin theta. And then if you divide these two equations, you're done. Just in case if you do not want tension, but if you want tension, you can do something more. You can square and add. So, and if you want tension for some reason, you can square and add. You can get the answer as AFR whole square plus mg. And even this is not required. You can simply say from the equation 1, the tension is mg sec theta, right?
Yes.
Yes.
Of course, you can express in the way you want, or mg by cos theta, and so on. Now, because we know the answer of repulsion force in terms of gravity and tan theta, so we can invoke the Coulomb's law now. So Coulomb's law can also give you FR, right? See, you're getting the repulsion in terms of gravity, but you can also get the repulsion in terms of charge, right? Which is
Yes.
1 by 4 pi q square by. Now, what is the separation between these charges?
Well side theta.
12 sin theta. That's the right answer. Very good. So this becomes 12 sin theta whole square. And you can see clearly that the Coulomb's law itself is giving you the answer. Which is q square upon 16 pi epsilon naught L square sin theta. Let's call the question 4. Now, what kind of question the textbook or the JE will ask? Okay, I have no idea. What you can do is, if you know the way of writing the repulsion in terms of gravity or other balancing force, and then writing the same in terms of the Coulomb's law, the next logical step is to equate these two relations and then end the calculation. So you can say from 3 and 4, what you can write? Q square by
Q square by mm,
and this is mg tan theta.
10 20.
Now let's multiply this. It looks big, but not difficult. So once you do so, the q square becomes 16 pi epsilon naught L square. Oh, pi, yeah, L square sin theta. L square mg. I think this is the full value, no? Yeah, correct. So we got something called 16 pi epsilon naught mg L square tan theta into sin square theta. Okay. And once we have this answer, this value, we can do something really interesting questions. So, okay, they may give you theta, they may give you separation, they will give you something and they will ask you something. That's the call of the textbook. But there is something interesting you can do, and that is called the small angle approximation. So, generally, while performing the experiment, the length of the thread is kept very, very long. So, for a very long thread, what will happen? If the thread is really long, then the angle will decrease. Do you realize this?
Yes, sir.
And this entire angle I can call as just 2 theta. And the separation which we were earlier writing as 2L sin theta, we can just call it x. Okay. And therefore, what else you can write is that angle theta equals to L by R. Okay. So the theta becomes x upon 2L. This is a new way of writing, and the separation is almost linear. So for a small angle approximation, the equation 5 implies q square equals to 16 pi epsilon naught mgl square into theta q. Can you say this? Tan theta is theta for a small angle, and sin square theta is also theta. I mean theta square, correct?
Yes.
What you can see that the relationship becomes really small. I mean really interesting. It becomes simple for a small angle, and we can further replace the theta by the q square turns out to be so this is how much 2 mg L. So q turns out to be the root of this. Okay, so now this formula we can write like this, which you can write as some constant into x power 3 by 2, where k is this entire term. Okay, now this is really simple equation. You can see from so much rigorous hard work, we eventually came across a formula which looks so simple. Okay. And what is the purpose of teaching all this? I mean, I have some interest actually. So I would like to introduce a simple concept called atmospheric leakage. So we believe that air is insulated, right? Am I audible, guys?
Yes, sir.
So we believe that the air is insulated, but it is not the case. Even during the, let's say in Mumbai, it's so much raining nowadays, or due to some thunderstorm, lightning, the air also attains a very weak but some sort of conductivity. So the charge on this pith wall, it was actually found experimentally that the charge on the pith walls over the maybe months or days, the pith wall started coming closer to each other. It's a very slow process, almost like you won't see if you watch for maybe a few minutes or 1 hour. But of course, if you come next day, you'll see that okay, the separation has changed. And why this was happening? Because the conducting air, which is also very poor, but some, as I said, some connectivity you can expect. So the charge from the pith wall started leaking back to the earth. So due to the atmospheric charge leakage, the repulsion decreased, and because of the decrease of repulsion, the pith wall is started coming closer because gravity is trying to bring them as close as possible anyway. Okay. So for this particular situation, we would like to solve a numerical. Okay, so now you can read this part. This is basically the question from the IE Eroder. Question number first, maybe second. Okay, this is question number 3.3. Okay, because we have the formula k equals to, q equals to k x power 3 by 2. So we are just supposed to differentiate this. So this dq by dt becomes the charge leakage rate, and if you differentiate this, it becomes 3 by 2 root x dx by dt. And because x is the separation between the charges, so this is the velocity of either separation or approach depending on the value is added or subtracted. And this relation was the question of Euler. So if
But
you
it
read,
is leakage, so it should be negative.
so dx by dt is also negative. Given this is negative, this is negative, which means it is approaching.
Yes.
Okay. So just read the question and you can solve. 3.3. So we are done with the 3.3. Okay. So now from Eroda, what we have finished so far? 3.3, 3.4 is done. Okay, so now we are going to do the 3.5. So what you can do is you can attempt maybe for 2 minutes, then I will solve.
Can you send the pictures of the song?
It's a circle program.
Okay.
3.4 we did yesterday only, actually, the last lecture. And today you're supposed to solve the 3.5 now. So then I will also go to the 3.6, 3.7, and so on. We will be finishing the entire Eroda in this particular chapter because that's very easy. These things are not difficult. And from Eurodaw, you can get some question JEE mains. Advanced is still more difficult than Eurodaw.
Hello.
Yes.
Sir, I'm not getting the sum. Can you tell the page number?
So electricity. I mean, sorry. Its name is electrodynamics.
Yes.
Part 3. Question number 3.5.
Three.
The fifth question in the electrodynamics part.
Okay, okay.
If you want, I can send you the.
No.
Okay.
Sir, is it a thin wire ring?
Correct. A
That
thin
one.
wire of yes.
Okay.
So we have done questions like this in other chapter also. What you're supposed to do is they are asking the tension force. So take a small piece of ring, you will get the answer. Anyway, you can try. I will solve. So anybody getting the answer?
Sir, I'm getting one number wrong from the answer. Like they are getting 8, I'm getting 4.
Okay, so just think more.
Yes.
So simple idea is, see, because you can apply the Coulomb law only for the point charge, so you cannot write the Coulomb law for the ring. So you
Yes.
can take an elementary portion of the ring and then try to write the FBD.
Yeah.
So that's it. That is something you need to think about. Okay, else I'll help. Take few more minutes. The whole idea is we cannot apply the force between the ring and the charge. So what we do? We simply take the small piece like d theta part of the ring, and then you can do the calculation. And again, this question is very, very powerful question. Like you can see, this question will have at least application in minimum 6 to 7 chapters of physics. So once you solve it here, you will face this question in magnetism, in EMI, in thermodynamics, in elasticity, viscosity, surface tension, wave in string. So wave and motion chapter. Then yeah, that is sufficient. And of course, circular motion, laws of motion, rotation. So this is a very famous question. That's why I put a star. Don't take it lightly. Just mark this question in your book and solve, and then you will realize that okay, this question is going to ask everywhere. Okay, I think I have given enough time now. So what we have is a ring, and this ring is charged with how much value? The total charge on am I audible, guys?
Yes.
Yes, sir.
So you're speaking.
Okay, I'm not audible.
Now you are.
Audible?
Yes.
Yes.
So what we have done is we have taken a small piece of ring, a small piece of ring, okay, and the tension is T. So now this ring with some charge, and this is also Q naught. So this ring will have a small charge. How much? We can consider dq
Yes.
because our angle is d theta.
Yeah.
And we know that tangent to the radius is 90 degree.
Yes.
So we are looking for the component of tension towards the center. So I'm looking for this component. So if this is d theta by 2, this is also d theta by 2. So this is how much? 90 minus d theta by 2. So what is the component of tension in the downward direction? Can you guess? Can you calculate? Not guess. So what is the component of tension in the downward direction?
Sine.
T sine
Yeah.
d theta by 2.
D theta by 2.
But sine of a small angle is angle itself. Can we say
Yes.
T d theta by 2? Now this is
Yeah.
the this is was the catch, and this is what you are supposed to learn. And the repulsion force, we can say dF repulsion outward direction. So for equilibrium, what we can write?
dF repulsion is equal to T D theta by
T d theta by 2 plus T d theta by 2, which
2
is
times. Yes.
T d theta. Now, next time in your life, you're not supposed to derive this. I mean, rather you should know how to derive, of course. But remember this answer. The tension component towards the center for the small angle is T d theta. It's very interesting answer. So it's a good idea either you remember this, but at least do this derivation few times to realize what we are doing. All right, so we got the repulsion, and how to write the repulsion? This is really like a dot. I mean, of course, the d theta is so small that this is like a dot. If you zoom, you can see something like this. So we can apply the Coulomb's law between the dot and the Q naught. Okay.
Yes.
So Coulomb's law says that it's 1 by 4 pi epsilon naught Q naught into dq upon r square. R is the radius and that's the distance. Now how to write dq? We can write dq proportional to angle. So dq by,
DQ will be R D theta.
yeah, dq by d theta is q by 2 pi, isn't it?
Yeah.
The charge per unit angle, or you can say length, will be same. That's lambda.
Yeah.
You can express the way you want. I'm just writing in terms of angle. You can write in terms of length also, because this is r d theta. It's the same thing. dq by r d theta is same as q by 2 pi r lengthwise, correct?
Yes.
And if you compare these two, you can clearly see what is dq now. So if I call the equation 1 and if I call this equation 2, from 1 and 2, what we can write? From 1 and 2, we are done, right? We don't have space. Huh? Okay, I'll go to the next page to solve this. So finally, what we have is 1 by 4 pi epsilon q naught into q by 2 pi into d theta upon r square equals to d d theta. And you can clearly see that d theta will
D
cancel out.
theta cut. Yes.
And now we got the tension force, which is very nice answer or very bad answer, maybe. It depends on your perspective. 8 pi
8.
square. This is our answer.
Yes. Sir.
Can you check the answer? Just confirm, guys. Is
Yes.
this the
Yes.
Yes.
pi square is there?
Yeah.
Huh.
Yes, sir. It's correct.
No, this was the error question. Can we make it better? Can we do something with this question? Yes, I got an idea. So I would say this is the, I mean, my modification to modified form. And what is the new question? Repeat the same problem, assuming a ring is having mass m and is rotating with an angular velocity omega. Okay, now just add this variant to add some spice to the solving. The rest part is same. Only one more force will act now. Which force?
Centripetal.
Correct, centripetal force. So now the tension will be more than before, isn't it? So can you find the tension now? Find T. Again, And now this time you'll get a different answer for sure. So please attempt this. If you have really understood the previous question, you should be able to solve this question. So you can think that who will provide the centripetal force? The repulsion is acting away from the center, so who will provide the centripetal force?
It will act with the TD theta, right?
Correct. So T theta is not just equals to repulsion, but it is more than repulsion.
Plus, yes,
Yeah. So that
that
the
force will be added.
yeah. So now you can think and then just to simplify this, tell me the answer. And these questions will become the question of wave and sound automatically. So you will, if when you will study the chapter of wave and sound, a ring having the tension, if you know the tension is T, and if you create a small disturbance in this ring, this will travel with the velocity v with respect to the ring, and the wave velocity we write as under root of T by mu. And because this is a big form of T, you can substitute and you get the answer. This may be the future J advanced question. But once you know how to do the basic, the other questions can be easily thought about, because what
But
we
so in this question,
yes,
which you gave now, in that d theta term will be there or not?
no, this will never come. Na. This is what you are taking to solve it. Na.
Yes.
So of course, if something you assume to solve it, it will not be
Okay,
the
got it.
correct. So tell me, guys, what is the new answer for tension?
Hello.
Yes.
Same thing first Q naught wala.
Yeah, this will remain as such. What else?
And I think minus m omega square r.
So why minus will come? And why m omega square will come? Like you're writing the ability for the elementary, right?
Yes.
So for elementary, what you're writing? I mean, you have to be careful. Net force, you write net force towards center equals to MAC, right?
Yeah.
But M is the elementary mass of that elementary taken, right? So this will be Tg theta. I can write directly now. The net force towards center is always fixed. Tg theta minus the repulsion is net force towards center. Dm into omega square r. The mass will be only the elementary mass, correct?
Yes.
So this part is clear. The net force
Sir.
equals to mass into acceleration. Mass is dm and acceleration is omega square r, right?
Yes.
So this will be k q naught dq, which is lambda d theta. I can just write like lambda r d theta, and we can substitute the lambda later on by r square. And dm we have to write also lambda, but now it's like confusing. I cannot use lambda for charge and lambda for mass in a similar fashion. I may make lambda q and lambda m r d theta mass omega square r. That's it. Now you can see d theta gets cancelled at once, and it will add up. Q naught lambda upon 4 pi epsilon naught r plus lambda m omega square r square. And now you can substitute the value of lambda q and lambda m. Okay. So what is lambda? The charge upon length of the entire ring.
Charge upon.
Am I audible, guys?
Yes, sir.
Plus m upon 2 pi small r into omega square. So this is how we can get the new answer, which looks really cool. Like tough question, right? Challenging problem. And we have answer m omega square r upon 2 pi. Okay. This is your answer. Okay. Now, can we solve something more from here? Yes, we can solve. We can find the change in radius of the ring given the Young's modulus as y. Now, I can bring the elasticity chapter also. I have shown you the wave chapter. Now, what is the how to use elasticity? Of course, you haven't studied, but if
The
you have
Young's modulus part, right?
the Young's
Yes.
modulus part, yeah. So, the Young's modulus part, the y is defined as the stress upon strain,
Stress by strain.
and stress is nothing but the force upon cross-sectional area. So, if since I am okay, what I'm doing is I am having a ring. Let me make a thick ring just for understanding. If you make a small cut into the cross section anywhere, if you zoom it, you will see a big cross section like this, right? Like a ring is this way, right? Just I'm zooming this portion, and the tension was acting this way. Now I need to give you the radius of the this cross sectional radius A, apart from the radius of the ring. So now the stress developed will be the tension upon pi a square. Now this is the question from elasticity. So once you know the tension in the this particular case of ring, this is the stress T upon pi a square. And from the Young's modulus definition, the stress is Young's modulus into strain.
Strain.
So T upon pi a square is y into, and still you can add as change in length of the ring upon original length. And for ring, we know the length will be proportional to the radius, and that is why we can actually rewrite as delta r by r. So as a result of this extra tension, the ring will stretch slightly, assuming it's made of a metallic wire. And I may be asking you what is delta r. So you get a really nice answer, I mean, as you perceive it. Tr upon pi a square y. And then the last step will be substituting the bad value of t which you derived. Okay? We can see how we can go from one question to the entire physics. Okay. So we can do something like this. So I hope this is clear, guys.
Yes, sir.
Yeah.
This is the from elasticity. So we can keep on hopping from the one concept to other concept if it is linked, and that is how the challenging problems are created. Like you know one basic thing, you know other basic thing, and the only difficulty is how to relate it. But if you can see something in deeper, you can actually you will be able to relate it with less stress. Okay. Okay. So all that we're done with 3.5, and that's why I said why this question is so important. You can now realize why this is so important. So 3.5 is the problem of aerodynamics. It's a versatile actually. It can be applied anywhere. Okay. What next? So now we are going to do some different variety of problem. And the different variety is called this we call two charge problem. In the analog in gravitation is called binary star problem.
Gravitation is the same thing like we're doing in the
Same, yes.
electrostatics.
Yes. That's why I will be teaching you gravitational concept and this in tandem to each other. And some left out part, I will take 2 or 3 lectures extra for gravitation to finish. So at the end of this chapter, you will gravitational chapter will be also over. And I will be sharing the separate notes for gravitation just for your convenience. So we have something called binary star problem. So first we'll try to understand why these problems are actually in place first. Why we need to study all these things. So we know that we have something like atom, and if you look carefully, in atom you have essentially a nuclei and orbiting electrons, right? So if I particularly talk about the H atom, then what do we have? We have exactly one proton and one electron, isn't it?
Yes.
So can we say this is like a binary charge problem or two charge problem? The answer is yes, we can say. So the way you study the like the atoms, you apply the Coulomb's law in the atomic structure chapter, which you start with in chemistry. You had applied the Coulomb's law, isn't it? And while applying the Coulomb's law, what you believed or you assumed that the electron is orbiting the nucleus, right?
Yes.
Isn't it? This is what you assume.
Yeah.
So if you look carefully, that this is like a in space, in empty space, we have just two charges which are orbiting around each other. Not one is orbiting the other; it's around each other. So in nature, they orbit around the common center of mass. Now, your idea of learning was slightly incomplete. Why? Because you don't. I mean, of course, you know now, but you haven't realized that the mass of proton we write as roughly how much? 1837. The mass of electron, right? So the proton mass is roughly 1837 times the mass of electron. Do you realize this?
Yes.
And if you remember the center mass concept, if we have a proton, if we have electron, I need to divide this line into 1838 parts. And then center mass will be somewhere here, right? It looks like the center mass itself is the proton, isn't it? So because of the tremendous mass difference, the central mass of these two charges is converging with proton, and therefore it is a good approximation to say that electron is orbiting the nuclei. So when this will not be true, if the electron, if I replace the electron with some hypothetically heavy particle, let's say if I bring some mesons. Mesons are very heavy. They are roughly 200 times mass of electron. Now the ratio is 9:1. So now I need to just divide into 10 equal parts. Okay. So now we can see that the center mass will be significantly different from the proton, right? Somewhere, let's say somewhere here. So now we cannot claim or say that the electron is orbiting the nuclei. That's, or no, we cannot say that the mesons will orbit the nuclei. That's wrong. So in physics also, in in atomic structure, when you study physics, atomic structure in physics at the end of this course, you will realize that the Bohr's theory we need to modify. So the previous derivation of Bohr's theory was based on the assumption that we have the H-like atoms, and for H-like atoms, the electron is definitely very lighter compared to the nuclei, and so the center of mass of the system will coincide with the heavier one almost, and therefore there is no need to say this explicitly that we are dealing with the two charge problem. We deal with the only one charge moving around the fixed charge problem. So the other charge got fixed in a way which was not the intention, right? Because of the mass difference, the one charge got fixed, other is like moving. So that's how we uh, learn the atomic structure. Now going forward, the JE will create a hypothetical particle. Let's say I gave you mesons. They will tell you that assume the Bohr's theory is written in a different way. The nuclei is not very heavy compared to the orbiting negative charge. The entire formula of atomic structure will be changed now. We need to bring something called the Rydberg constant for such system called R mu. And the Rydberg constant which you studied earlier was called R infinity. So now this will be replaced by this R mu, and then we will have a different set of concept. The mu is called the reduced mass. And this is called the conversion formula. So everywhere, first of all, to derive all formula, you need to go back to the chapter of what is it? Atomic structure. You need to go back to the chapter. You need to go back to the derivation, and you have to express the answer in terms of Rydberg constant, and then replace the R infinity in terms of R mu by this substitution. That is called the modified Bohr's theory, and of course that is the part of JE Advanced for sure. You have to be careful about the questions like this. So this two charge problem is the basis for the same. Similarly, we have the binary star system. Okay, so I would say, and we have something called baryonic center in the same fashion. Bariatric, I don't write the right spelling. All has to do with the like binary. Okay. So what we are going to learn that what happens if two charge moves under the influence of each other's force of attraction, or how the planet move under the mutual attraction of gravitation. It's easy for you to understand in terms of gravitation. So let's say we have two mass M1 and M2. Let's say we have two mass M1 and M2 and they are attached or not attached. They are actually moving in space due to their mutual gravitational attraction. Now, why the motion is necessary? Try to understand this. So, what happens if you don't move? If they only attract each other, they will eventually collapse, isn't it?
Yes.
So, how to maintain the separation between them without touching them? What we can do so that they should not come closer? And that should happen perpetually without any interference. How this can be achieved? It's very simple. Give them velocity perpendicular to the line joining the masses. So you can give V1 and V2. Now you may be asking why V1, V2, why not V1 only? Why not V same? Because the motion always occurs about the common center of mass. So let's say if the common center of mass is here, the M2 will move in the circle of radius R2, but M1 will move in the circle of radius R1. So this will end up creating the two concentric circles where the center of mass is same. Let me do it like this one. Like this. Okay. So what will happen? As the time will pass, they will remain at the same separation and turning like this. Do you realize this?
Yes.
And the velocity will be same. It will have V1, this will have V2, like this. The gravitational force will provide the required centripetal acceleration, which will let you move around the common center of mass. And because they remain on the same line, so the angular velocity of this line will be constant, right? This is
Yes.
called omega. Omega is something which is common for both the masses. So similar thing will also happen for the charge particle if they are. So if we have a positive charge, let's say the very famous nuclei, and a negative charge, let's say the very famous electron, if they will not move, what will happen? They will collapse. So the existence will be over, right? They will no longer exist if they collapse, because once they collapse, both will neutralize each other, right?
Yes.
So how to maintain their existence without affecting their polarity or and separation? The only way is perform circular motion about common center of mass. Do you realize this? Yes or no?
Yes.
So if I choose the separation between them as D, you can see we have the left question. Let me go on the next page, a bigger one. The idea is clear why we need to study this part,
Yes.
so that the two attractive objects can coexist without hitting, without colliding with each other. That's the idea. What is the idea? Such that the two attracting bodies, masses, particles must maintain the separation. and coexist as well. And for this to happen, the circular path is not necessary. It is also possible with the elliptical path, as we can see for the case of sun and the planet. So elliptical motions are also possible for any system which is coexisting under attraction. The only problem with the elliptical path is the separation becomes variable, fluctuating. So the circular path makes sure that separation is also maintained. Is this particular, guys?
Yes.
Okay. So let me draw this line. So what we'll do is we'll assume one as plus charge, but other as minus charge, because that's then only they will attract, right? The charge will have this problem. For mass, they can attract without any polarity issue. Okay, let's say this is the question. Now I need to assume the mass also m1, m2. So now the common center mass we can find easily, and in fact, I hope you know. For two mass problem, what is the R1 R2 value? So R1 will be m2 by
M2 by M1 plus M,
and R2 will be.
M1D upon M1 plus M.
So if we have R1 R2 values known in advance, okay. So no matter what is the radius circle, the center will be common. So these all will form concentric circles, right? So now what we'll do? You can write the ABD for any one charge. That's sufficient. So the attraction between them will provide the required centripetal acceleration. So you can just write the simple answer. If A equals to M, you can write for anyone. Which one you want to write? M2 or M1? I will
M1
write for both. M1 omega is for R1 or M2 omega is for R2. You can choose whatever you want. And the force of attraction you can write as K Q1 Q2 by D square. That's very simple. And the R1 we can write as M2 D by M1 plus M2. You can choose anyone to write, and you will see something really interesting. The force of attraction, I'll just show at the end. This is easy to remember, not to be worried. So K Q1 Q2 upon d square, and you can see clearly what we are having here is the reduced mass, right?
Yes, mu.
So this entire equation we can write in a very nice fashion. It's written as the force of attraction is the mu omega square r, and r will act as a d. This is the shortcut to remember this relation. You can do it in one line next time. And what you can do next is you can just simply substitute the value. Okay. So the reduce and the force will be mu omega square d, and then you can see you can get the omega value. So omega square is how much? Okay, I'll just start in short. F by mu d. Let's remove it under root. And if you substitute all values, you'll get the answer as, okay, it's a big answer. So you can see the omega turns out to be how much? The angular velocity. So they will be asking you omega and maybe the time period, like how much time it will take to complete one circle around each other. So the answer is 2 pi by omega. I hope this is clear, guys.
Yes, sir.
Yes, sir.
Yeah.
So now we can go. The two charge problem is you can do it for the gravitation also. In gravitation, it's really fun. I mean, interesting because in gravitation, what you can write? The shortcut is F mu equals to mu omega square d, the separation. Okay. And the F mu becomes G m1 m2 by r square or d square. And the reduced mass is how much? M1 m2 by into omega square d. You can see m1 m2 cancels out. So omega will have really nice format. So pretty easy to derive. And this relation is particularly of some interest if you want to observe something. The answer depends on the sum of the mass. Sum. So can we say this is the total mass of system?
Yes.
So if we have a planet of mass m and 3m, or if we have a planet of mass 2m and 2m, if the separation is same, the time period will be also same, right?
Yes.
Because you can see the total mass of the system is 4m, right?
4m. Yeah.
Yeah.
So the d is same, g, capital G is same, 2 pi is same. So as long as the sum is constant, the time period will be same. That's very deep observation if you have to understand. That the time period, nothing, I mean, it does not depend on the individual mass, rather the sum of the mass. And therefore, if you know this relation, you can answer the questions like this without solving. I hope this is clear, guys.
Yes, sir.
Yes.
Now, from the like two charge problem, we can go to the a system with more than two charges, 3, 4, 5, 6, whatever. And we can do similar calculation. So anyway, I will share the notes. You can just go through these repetitive questions to just understand what we are discussing. So now we'll do the equilibrium in 3 dimensions. Okay. So generally, I mean, none of us have the practice about the 3D diagrams and plotting them and solving the question. But 3D is really interesting because this gives you the idea of, you can say the sense of visualization. Like to solve any 3D problem, the first difficulty for every student is, can you visualize the situation? And how it comes? It comes through only practice. So as a student, even I used to think, and I really used to enjoy like 3-dimensional questions. In 3D problem, you need to have the perspective to plot the variety of views, like top view, side view, front view. So the view is very important. One should be able to, after reading question, should be able to see the same diagram from multiple perspectives. Like how the thing will look like if I look from the top, if you look from the sideways, and so on. So it's the same problem. Like we have 3 identical pith walls. Now, the moment if you have the 3 identical pith walls, they will repel each other. And because
Yeah.
they're identical, so it must be symmetrical repulsion, isn't it?
Yes.
So if you look from the top view, what you can see, how the top view will look like. The top view means from this side. So these 3 masses must be part of which kind of circle? Oh, circle. I'm saying triangle. Which triangle you can say? So these 3 masses will be forming the equilateral triangle, isn't it?
Yes.
So the top view will look like this. Bad choice of color. So this will be the top view. This is the view, right? Now I hope you can see this. It is clear. The 3 masses are like this. So do you realize the top view?
Yeah.
So now these are 3 charge particles Q, Q, Q. And therefore the net force on any charge particle, if I think of this particle, we have derived this net force, right? F,
Yes. 2F cos 30.
correct. So the answer turns out to be root 3F, right?
Yeah.
2F cos 30, which is root 3.
Yes.
So not like nothing extraordinary has happened. The only difference is the net force on, if you do the ability of any one charge, the net force will act like this, which is now root 3F, which you need to derive from the dimension of the triangle. And the gravity will act like this. And now I have to do one more thing which I haven't, which is the vertical. This is the thinner. This is the vertical which I have done in the plane of triangle. And this angle is called the angle with vertical. This is theta. This is called length L. So this will be how much? L sine theta, correct?
Yeah.
And this is a by 2 because a is not given, L is given. So we can say a by 2 is basically L sine theta cos 30.
Yes.
So basically a turns out to be root 3 L sine theta. You can see we are able to find the side length of the bottom triangle.
What you did, L sin theta into cos 30.
Yeah, this component.
Okay. Okay.
L
Yes.
sin theta into cos, because this is L, this is theta.
Uh,
So I use the vertical triangle to get L sin theta, and
yes.
then I went back to the bottom triangle to get the side length.
Got it.
Now this is the difficult part for any beginner, writing the components. But once you are done, this repulsion force is same, mg is same, and so on. So we can directly write Fr equals to mg tan theta. I'm not solving because I believe you understand this is.
Yes.
And what else? The Fr we can write in terms of Coulomb's law. A q square by a square, and a I have written in terms of L eventually, and then so on and so on. You can substitute and you can get the final relation, which is not difficult. Okay. So we can get the answer like this. Okay. Now this kind of question is something which you need to practice to understand that if I bring it 4 pith balls, the bottom will be square. If I bring 5 pith balls which are identical, the bottom will be pentagon, 6 hexagon, and so on. Okay. So if you have n identical pith balls, so the bottom will be n-sided regular polygon. Is this clear?
Yes, sir.
All right. So this is the 3D part. Now you are able. Now you can solve thoroughly all questions uh, up to what? Okay, 33, 36, 32, 33. So the next lecture I'm going to start the electric field. Okay.
Sir,
And then
rotation doubts when we can keep the picture.
we can keep extra. So you guys are ready, then we can
I'm
keep
ready.
we can keep on Sunday 1 hour early.
Yeah, fine.
Yeah, let's say because you have lecture from 6 o'clock. So those who are having doubt, they can join me at maybe 4:30 or 5 o'clock.
Okay.
This Sunday, of course, not possible because okay, this Sunday I have examination. I have to go somewhere.
Good.
So this Sunday we will have lecture only. So we can keep on maybe Tuesday early.
Tuesday early fine.
Yeah, by that time you should be able to finish.
Yes.
Okay. So yes, Kanu, you can leave, not an issue. Yes. Yeah, question 33 up to, yeah, from SCV. And I think you had one doubt.
Yes,
Is
sir.
the doubt solved now, like from the discussion, or no? That is different, right? What was the question?
So it was question 28. Let's see.
Just dictate it and I can solve right away here. So there are two masses, no? Like two masses with a spring.
Yes, sir.
So masses are identical or different mass?
Sir, 1 second.
So in this, I think we need to just equate the forces, spring force and Coulomb force.
Correct. So if
Yes.
the initial length is L naught, the new length will be L naught plus X. So after repulsion, what will happen? The length will change to L naught plus X extension of the spring because of the repulsion. So the repulsion force is how much? K Q square by, and this must be balanced by the spring force. Or this K is spring force. This K is confusing force. So you can directly write as 4 pi upstream. Like simple like this.
Yes, sir.
What is asking? The time period of oscillation, something like that.
They are asking the extension. I think.
Extension and length.
Extension. So you can use. So this is somewhat binomial. If it is given, I think I know this question should be like this only. L naught plus x power 2x. This we can write as. We can take L naught common, so a square 1 plus x by L naught. Then we can use the binomial approximation 2x by L naught into x. Then we can attach L naught plus 2x. Or you can multiply this. So this looks like some sort of quadratic, right?
Yes, sir.
Maybe now you can solve, because earlier we cannot solve because it was like some cubic equation. Cubic? Yeah, now it's like quadratic. Now we can solve, right? And you can try.
Yes.
Let me know.
Yes.
I
Yes.
haven't tried the question. I don't know what I'm doing. But anyway, something like this will help. Okay. So now please finish up to 33. Next lecture I will start electric field, which is pretty much common like Coulomb's law, and then we'll do a lot of derivation in the electric field. Okay. Okay.
Thank you,
Bye.
sir.
Take care.
Thank you so much.
Thank you, sir.
Good night, sir.
Bye, sir. Thank you, sir.
So good night.
Good night.